Welcome to the Earth Science Classroom. Welcome back. This is the astronomy playlist. We're looking at Kepler's second law of planetary motion. And this video is going to cover what the law is, how it relates to the first law, why we need, basically why and how this law proves or gives proof to planetary motion, and leads to obviously Newtonian physics. Should happen a few years in the future from this, and looking forward to the third law as well as more like of an overview. All right, join me now. So what is this? Well, it's called the law of equal areas. And basically what we have is we have our ellipse, we have our sun as one of the focus, and the empty focus would be over here, right there. And we'll have a planet, let's say right here, and let's do Earth. Okay. And you know that the ellipse has both a minor axis and a major axis as two different lengths. This is the minor axis, and this is the major axis. There we go. And we have the foci as well. And we have the eccentricity, which is the measure of how elongated the ellipse is. And a circle is a special kind of ellipse. So we're looking back at the first law, which was in 1609. Don't forget that Kepler was hired by Brahe in Copenhagen in the year 1600. Brahe then passed away in 1601, leaving all the information and notes of Brahe's for Kepler to use, and then to find a pattern and math to be applied to these notes. So the first law came out in 1609, and the second law, which kind of like followed straight on. So once he figured the first law out, he could then use that first law as a foundation to push on and then work more with this shape, work more with the planetary motion, especially Mars as his main planet to study, and then track the motion of the planet each day and each night, and come up with this new law called the law of equal areas. Okay, so now based on the ellipse, this law obviously came out in 1609. There is a perihelion. Again, helion based on the sun. Peri means near in Latin, so there's a near point of that planet, in this case Earth, in relation to the sun. So it's the point where the Earth is closest to the sun on its orbit or revolution. And there's also a point over here where the Earth is positioned the furthest away from the sun, which is called the aphelion. And this is unique, well, not unique, but it is related to ellipses and not circles, because there's two different lengths. So what we have here is Kepler observing the planetary motion, especially Mars, and watching it as it goes around on its revolution orbit around the sun. And what he noticed was that when the planet was at perihelion, then if you were to have a line, right, there we go, so a connected line from the Earth to the sun, and let's say as the days went on and nights went on, weeks and weeks and weeks, the planet, in this case Earth, is going to continue on its path, on its orbit around the sun, complete one revolution. So a course of a couple of days, the Earth's going to move in relation to the sun. So what's going to happen is, because it's close to the sun, that, let's say it moves, okay, at a certain time, right? So over a certain time, let's say 3 weeks, Okay, it's going to move, and then after 3 weeks, Earth will be here. So if we were going to draw a little line and then connect and shade in that triangle, that area, the area covered by the movement of the planet, in this case Earth, over a certain time. That's what that area stands for. Basically, it's just showing you that this is the distance covered and the area covered over a certain time of that planet on its revolution around the sun. Now, if we take Earth at the perihelion, when it's far away, because you've got a much greater, I'll just do the triangle in green, you've got a much greater distance from the Earth to the sun. And over the same time period, the Earth, say 3 weeks, the Earth isn't going to move as far. There's a decreased distance traveled on the revolution when it's far away. So if you were, again, to connect the 2 points, start to finish, of this time period, and then shade in the triangle created, and this area, he found out that when the planets are at different positions in the orbit revolution, perihelion versus aphelion, that the size of the area drawn is exactly the same. So this triangle and this triangle is the same area, same value of area. Okay, let's just call it x and x. It's the same. Why? It's because of the ellipse being a certain shape, because the sun being a certain focus, and the fact that the Earth is at perihelion versus aphelion. He's found that the planets would change speed or velocity at different points along the revolution, along the orbit. And it corresponded that at the aphelion, the planet is going slower, and at the perihelion, the planet is going faster. It covers more area when it's closer, and it covers a less area when it's far away. So what you have is he discovered a change of speed. Now, this was done way before Newton's Principia of physics of gravity, which came out in 16. So Newton published his in 1687, and once I'm pretty sure that Kepler's work got to Newton, and Newton kind of like used that as well as a foundation or a stepping stone towards his gravitational theories and laws. However, gravity can explain this motion, this change of velocity due to the distance, between the Earth and the Sun, and the strength of the gravitational attraction. So, but Kepler noticed it and took note of these different speeds, and then obviously Newton just applied gravity to cement this planetary motion. So the fact that he did this in 1609 with a basic telescope on Earth with limited resources and just his brain, his eyes, and the ability to note down and be aware of these subtle changes every night, and be able to figure out and combine all these notes to one revolution, 1 year, actually with Mars in respect to the motion, was incredible. And the fact that it works out with today's technology and knowledge and science and Hubble telescope and all that good stuff, still works out today. This guy Kepler was just a genius. I'm sure Brahe was equally talented, but Kepler really just set the ball in motion for all these amazing theories and laws to be discovered by mankind. Obviously, Newton really putting the cherry on top with gravity to cement all these ideas. But this is basically planets changing speed based on where they are in the orbit and the fact that they go over a certain distance over a certain time, the areas inside the ellipse or the orbit are equal. Again, the law of equal areas. All right, guys, thanks a lot.